Welcome to the Chapter 4 Subskills for Trigonometry. We are going to look at transformations of functions, look at how to identify when a function is increasing, decreasing, or constant, and we will review or preview factoring. So to start, we're going to look at transformations of functions. I'm going to utilize Desmos, and we're going to use the parent function of y equals the square root of x. And here is a graph of y equals square root of x. We could always plot points to determine this graph, but for now, we'll just take a look at what happens once we have this graph. What happens when we add to that function, add to that square root function? So take a look at this first one here where we have y equals the square root of x minus 3. So notice in this case, the minus 3 is inside the function, in with the x. And so you might guess what might happen, and you think, okay, well, it is in with the x, so maybe something about something horizontal. And let's just take a peek and see what happens there. So when we graph y equals the square root of x minus 3, notice our graph shifted right 3 units. So it seems a little counterintuitive because minus 3, you might think, minus or a negative takes you to the left, but that minus 3 in with the x actually takes you to the right 3 units, and otherwise the graph stays the same. So if we now switch it from x minus 3 and we turn it into an x plus 3, we may have an expectation, and now we are going to the left 3 units. So the way I like to describe adding and subtracting in with the x is we move left or right. Our graph is translated left or right, but we go in the opposite direction as the sign. Okay, so that is a horizontal translation. Now, what happens when we add or subtract? But now it's not in with the x, but it's outside the function. So the square root of x right here is on its own, but the plus 2 is outside the function. So you might take a guess, and let's find out. So if we have, right now we have the square root of x graphed. And now when we graph the square root of x plus 2, now our graph shifted up 2 units. So you can see we just moved up 2 units. Each point moved up 2 units. So now you might have an expectation. If I change that to minus 2, going back to our original function, and then if we change that to a minus 2, now we go down 2 units. So what I like to say for this, if we have this adding and subtracting outside the function, we move up or down, or we shift up or down, but now we go in the same direction as the sign. So the minus 2 translated us down 2 units, and negative 2, that's intuitive. That's that same direction you'd think down to. So now let's take a guess if on this next function here, where we have y equals the square root of the quantity x plus 1 and then minus 4. So how do we handle this? We go one at a time. So we can see there's adding and subtracting inside the function. So that's going to take us left or right, opposite direction as sign. So since it's plus 1, that will show us that we move left 1 unit. And then we have the shift, something that -4 is going to cause another shift because it's adding and subtracting. So here we have this -4 is adding and subtracting outside the function. So that will shift us up or down, same direction as sine. So in this case, that -4 will take us down 4 units. So let's check to see if that is in fact what we get, and look at that. So you can see that point at the origin, the original point at the origin, then we shifted left 1 and down 1, 2, 3, 4 to get that new point. And that's true for all of the points on that red graph. They would shift down or left 1 and down 4. Okay, so that is it as far as translations go. That's where we don't really change the shape of our graph, but the graph is moved left or right, or up and down, or both. Now let's take a look at what happens if we have a negative multiplier. So in the first case, we have this number 5 here. Y equals the negative square root of x. So you may have, you may pause, take a guess, think of what might happen, and let's take a look. Okay, here, instead of opening or increasing here, we're now instead going down. And what we will describe that is, how we will describe that is a reflection of your original graph over the x-axis. And so if you take that red graph and you reflect it over that x-axis, you will get y equals negative square root of x, or that purple graph. Next, let's go ahead and look at y equals the square root of negative x. Now, again, you might take a guess. Well, if the negative was outside the function, we reflected over the x-axis, what would happen if we have a negative multiplier inside the function, or multiplying by x? Okay, so let's see what happens when we graph y equals the square root of negative x. So when there is that negative multiplier in with the x. Okay, and now we see that the graph is reflected over the y-axis. And another way we can describe that, it's a little less traditional, but it's also just a different way of describing it. Here you can see this is a horizontal reflection. So you're reflecting horizontally, and that's in with the x, versus this one right here is a vertical reflection, and you can see that's outside the function. So just different terminology to describe the same thing. The more standard description is when we have that multiplier outside of the function. This is a reflection over the x-axis, and when that negative multiplier is in with the x, we often will call that a reflection over the y-axis. All right, and last but not least, let's take a look when we have a multiplier outside the function. What do you think is going to happen here? So notice this is different than what was happening up on 3, where we had subtracting 2. Now we're multiplying by 2. So again, all of our shifts whether it was in the function or outside the function, all of our shifts are seen through adding or subtracting. But now we have a multiplier. Again, you can stop and think, what do you think that might look like? And let's take a look. When we graph y equals 2 times the square root of x, now we don't shift anywhere. However, we grow faster. In this case, what we'll call that is a vertical stretch by 2. And what you can see is you can see that any of our points, like here, our y value is 1, and then right above it, we get the y value is 2. So we have that multiplier. So notice the same x value, but our y goes from 1, multiply it by 2, and we get 2. Similarly, if we have that 0.242, the x value will stay the same, but our y value will double. So we may have, or up here, we'll have that same x value of 4, but now instead of 2, we'll double that and get 4. And one more, we'll just take a peek because it's a little bit harder to see here. But if we take that 0.93, the x value will stay the same, but the y value will double to give us 6. And that will give us that point right there, 9, 6. There we go, 9, 6. And then now if we change that 2 to a -2, that's actually a case where we have 2 things going on here. We have both the vertical stretch, and because there's that negative multiplier, it will be a reflection, or a vertical reflection, or a reflection over the x-axis. So that's each of those in isolation. So now let's take a look, and this will be here for your reference. So you can always rewind back and look back at this, or if you have the notes printed, you can look at this. But just real quick, here, if you have adding and subtracting outside the function, that's going to be a vertical translation or shift up or down, same direction as sign. If you have adding or subtracting inside the function, in with x, that's going to be a horizontal translation, and that will shift you right or left, but the opposite direction as the sign. Now, if you have a multiplier outside the function, that's going to be a vertical stretch or a vertical shrink. And actually, let's go back real quick. I meant to show that as well. If we have 2, but instead we make that like a fraction, oops, like 1/2 instead of stretching it by 2, now it will be a vertical shrink by 1/2. So where our, oops, let me go in a little bit more. Where we had the 0.42, now our x value stays the same, but the y value will be multiplied by 1/2. So we'll just get 4(1) as that showing that vertical shrink. And all right. And then we can also have horizontal stretch and shrink. I'm going to go over that, or kind of skip over that one a little bit. Just actually, let's go and take a look at Desmos with that. And we're going to address horizontal stretching and shrinking a little differently with our trig functions, because there's kind of a key feature, the period of our trig functions, that are addressed with our horizontal stretching and shrinking. But I do want to quickly show that as well. So let's take a peek. What happens now if our multiplier is in with the x? So we're going to have a multiplier, but in with the x. And so here, what's going to happen is if we think about it horizontally, now multiplying by 2 inside the x actually shrinks us horizontally. So it's almost like squishing it side to side. Versus if we have a half in there, now this will vertically or horizontally stretch it. All right. So again, when it's in with the x, it's a little bit counterintuitive. So the half actually will horizontally stretch, whereas the 2 horizontally shrinks. And then last but not least, we have our reflections. So when you have a negative multiplier outside your function, you will reflect across the x-axis, or a negative multiplier in with the x will reflect across the y-axis. So let's go ahead. We're going to graph z of x equals negative the quantity x minus 2 squared plus 3. And first and foremost, let's identify any of the transformations that are taking place here. So we're really focusing on the transformations as part of the graph. So our adding and subtracting in with the x, that's going to be a horizontal shift. And so because it's in with the x, it will go left or right, but opposite direction is sign. So the minus 2 will actually shift us to the right 2 units. So we'll shift right 2. The plus 3 outside the function is going to be a vertical shift, up or down, same direction as sign. So the plus 3 will actually take us up 3 units. And last but not least, we have a negative multiplier in front of our function. So it's outside the function, not in with the x, but outside of that x squared. And so that is going to reflect over the x-axis. Okay, so we reflect over the x-axis, we go right 2, we also shift up 3. And because we do not have any multipliers outside our function, we do not have a vertical stretch. And because we don't have any multipliers inside our function, or multiplying by x, we will not have a horizontal stretch or shrink. So now the other piece we need to do, because now we're no longer dealing with a square root function like I was showing on Desmos. Now we are going to take our parent function y equals x squared. And ultimately, we would love to be able to just quickly sketch that. But if not, we can always plot points. So for y equals x squared, we can plug in 0, or I'll just do the classic, -1, -2, -1, 0, 1, 2. And although the goal is to not have to plot all of these points. So we're going to square -2 to get +4, square -1 to get +1, 0 squared equals 0, 1 squared equals 1, and 2 squared equals 4. So that is our parent function right there. And so we get, I'll just plot those points. And that gives us this shape of a parabola. Okay, so now because we just have reflections and shifts, we can go ahead and just reflect over the x-axis, and that will be that first reflection. So the 0, 0 will stay there, but if I go over to x equals 1, instead of going up 1, now I will go down 1. Same thing at x is -1, instead of going up 1, I go down 1. And then over at x is 2, instead of up 4, the reflection will take me down 4. And similarly on the other side. So now we have just the reflection. And now what we can do is we can take that orange graph, that reflected graph, and shift it right 2, and up 3, and that will give us our final graph. So we're going to take each point, I'll start with the origin, and shift right 2 and up 3. Again, I'll go to the point that was at 1, -1, and I'm going to shift right 2 and up 3. And over here, right 2, up 3, and the last 2 points, right 2, up 3. And if it is confusing with any of those other points, you're always welcome to erase any of your previous graphs. And now we're going to draw a nice smooth curve, which gives us that parabola opening downward. So that is the graph of z of x. Using, and in this case, we really were utilizing the transformations to get that graph. Okay, next, here we go. Let's now take a look at f of x equals the square root of -x minus 3. Now on this function, it can be helpful to remember the domain. And the reason why I think this is nice is that could help us kind of confirm any reflections or shifts. So you may recall that we cannot find the square root of a negative. So if I try and find the square root of -25, there is not a real number where if I multiply it by itself, I get -25. And you might think, well, what about -5? But then if I multiply -5 times -5, I will get +25, not -25. So the square root of -25 is not real. It's not a real number. Okay, so then what are we going to do? Well, we need to confirm, or we need to make sure that we only put positive numbers into our square root. So essentially we can say, oh, well, we know that -x has to be, or it's not allowed to be negative. So it must be greater than or equal to 0. And now if I wanted to solve for x, I could write that -x as -1x. And to get x by itself, I could divide both sides by -1. However, when I multiply or divide both sides of an inequality by a negative, I have to be sure to flip my inequality symbol. And 0 divided by -1 is still 0. So essentially, this is telling me that my domain will only be to the left of the y-axis because x has to be less than or equal to 0. So that might kind of help confirm some of my transformations as well. So let's take a look. When we have a negative multiplier that is multiplying by x, that is going to be a reflection over the y-axis, or a horizontal reflection. In addition, when I have adding and subtracting outside the function, I will shift up or down, same direction as sign. So that's going to shift me down 3 units. And there are no multipliers outside the function, so no vertical stretches or shrinks, and no multipliers inside the function except for the -1, which we already dealt with. And so there's no horizontal stretch and no adding or subtracting inside with the x, so no horizontal shift. So here, if you don't know your parent function, it's going to be that y equals square root of x. That's the basic one. And you're always welcome to make a table. So think of numbers that are nice to take the square root of. So 0 is nice, 1, I don't want to take the square root of 2 because then I need to get out a calculator and get a decimal, but square root of 4 is nice. So now we just plug it in. Square root of 0 is 0, square root of 1 is 1, and square root of 4 is 2. And now we'll plot that parent function. And that's just that parent graph. Now we will go ahead and reflect over the y-axis to get that intermediate graph. So the origin stays. And then now this 0.11 will reflect over, and instead of going right 1, we'll go left 1. Same thing, the 0.42, instead of going right 4, I'll stay at that same y value and reflect over that y-axis and go left 4. And so this is an intermediate graph right here, the orange. And now I will shift down 3 units, 1, 2, 3. And so I'm taking that orange graph and just taking each point and shifting down 3 units. Again, take that 1 or negative 1, 1 and go down 1, 2, 3 units. And that last point down 3 units. And that will give us the graph of f of x. Okay, let's go ahead with one more. So now, we have a lot going on here. We have f of x equals -2 times the quantity x plus 1 cubed minus 2. So in this case, we now have our parent function here is going to be y equals x cubed. And this one might be a little less familiar. Again, whenever in doubt, you can always make a table for your parent function. And the goal is to eventually get more and more familiar with this. So we have to do less and less on that parent function. But just to get a feel, we'll plug in -1 or -2, -1, 0, 1, and 2. So -2 cubed is the same as -2 times -2 times -2. So we get -2 times -2 is 4, times another -2 is -8. And -1 cubed is -1 times -1 times -1 gives us -1. And 0 cubed is just 0. 1 cubed is 1, and 2 cubed is 8. Now you can see that not all of these points fit on this graph, and that's okay. Maybe I should get a better graph, but a bigger grid, but really it's just to understand that it's going to go up fast or go down very quickly. So here I'll just kind of sketch -2, -8. And there we have our parent function y equals x cubed. Okay, so let's now identify some of these transformations. So let's start in with the x. Inside we have that adding 1. So because it's adding and subtracting, we're going to get a shift. In with the x, adding and subtracting takes us left or right, opposite direction as sign. So that will take us to the left 1 unit. So that will be a horizontal shift, left 1. Then let's look at this multiplier. Our multiplier, -2, actually will cause 2 different transformations. The negative will cause a reflection, and because it is outside the function, it will reflect over our x-axis or reflect vertically. But the 2, that's a multiplier outside the function. So that's going to be a vertical stretch. So we have a vertical stretch by 2. And then last but not least, we have this -2 outside the function. So again, adding and subtracting will always be shifts. And when it's outside the function, we will shift up or down, same direction as sign. So the -2 takes us down 2 units. And here we go. So this is a lot of information here. And so one strategy that works when, especially if we don't have a horizontal stretch and a horizontal shift at the same time, but one thing we can do is we can just take our y values and multiply them by the -2. And if we do that, we'll deal with both the stretch and the reflection all at once. So if we now multiply all of our y values by a -2, and we end up getting, various y values here. Let me just compute those. So we get 16, 2, 0, -2, 16. What we'll see if I'll graph that as an intermediate step here. So if I have 0, 0 still, and I'll make sure to graph -1, 2 and 1, -2. All right, and then the next point, 2, -16 would be very, very far down, or the same thing, -2, +16, very far up. So I will just emphasize that by drawing it nice and steep. So this is the intermediate graph, and now I can go ahead and shift left 1 and down 2 to get my final graph. So here I'll take that green graph and shift left 1 down 2. And again, each point, left 1 down 2, left 1 down 2. And I want that, notice the origin shifted to that -1, -2. So I really want that to emphasize that that's where that transition happens. And in this case, the orange graph is the graph of f of x. Now, in my opinion, transformations are the most useful when it's a combination of shifts and reflections. However, just knowing what the transformations do will help verify that the graph actually makes sense. And so it's nice to have knowledge of all different transformations, but where the real value comes in with the transformations as a graphing tool, to me, the most useful are your reflections and your translations or shifts. Okay. Next, let's take a look at the graph of functions and identify when those functions are increasing, decreasing, and constant. So, for example, number 2 says, use interval notation to write the intervals over which f of x is increasing, decreasing, and constant. So first, let's just talk a little bit about what does that mean for a function to be increasing, decreasing, or constant. Well, basically, when I look at a graph, I want to be careful not to look too much at these arrows. In the sense, I mean, those arrows are important. It means that the graph continues on in that direction on either side. However, when I'm looking at increasing, decreasing, or constant, I have to make sure that I'm looking from left to right. So as I move left to right on this first section of the graph, as I'm going from the left side to the right, I am moving upward. So this section of the graph is increasing. Okay, and then we're looking for another section where as I move left to right, I go up. So look at this section right, this middle section here, that's as I move left to right, I'm staying the same. I'm not going up, I'm not going down. So that's going to be where it's constant. Let's look at that next window. So here, as I move from this left side to the right side, in this case, I am going downward. So that will be decreasing. And let's keep going. That last piece, as I move from the left to the right, again, I'm going up. So in this case, it is increasing in both of these pink sections. So now we have to know, how do we describe this? And what's really important is that we kind of the standard is you will describe when it is increasing, decreasing, or constant in terms of X. So, for example, I'm really looking, okay, I have to describe this section in terms of just the X value. So one thing when you're trying to get the hang of it, you may consider is drawing the coordinates or just writing the coordinates of each of the transition points. So in between that pink and blue section, that coordinate is -2, -1. And then in between the blue and green, that section there, or that point there is 0, -1. And in between the green and pink, that's that point, 2, -3. So that will help us identify, okay, we're only interested in the X values. So we're going to be using that -2, the 0, and that +2 to describe when we start or end each interval. So let's take a look. This function is increasing, and notice this arrow here shows that it goes on. It continues to all the way to the left, that all that section is always increasing. And then we stop here at -2. So we will write that interval as -∞ to -2. But there's another interval. So we use that U to indicate union. And over here, we start when X is 2 and we go to the right. And again, that arrow indicates that we keep going. So that will be 2 to infinity. Now it is decreasing. Or just before we move on, because sometimes that can be a little confusing, notice this is using interval notation. So this is not a coordinate of any points here. The black, I list coordinates of actual points. However, this is an interval, and it's saying when X goes from -∞ to -2, my function is increasing. Also from 2 to infinity, the function is increasing. I'll go ahead and erase those intervals so we can now focus on when it's decreasing. So that's that green section there. And we're going from 0 when X is 0 to when X is 2. So the way we describe that is 0 to 2 with parentheses on both sides. And then last but not least, it is constant in that flat section. But again, in terms of our X values, it's going from -2 to X is 0. So we denote that as -2, 0. Again, this is an interval from -2 to 0. That section where X goes from -2 to 0, that section is where our function is constant. And also another standard is that we use interval notation, or when we use interval notation to describe where a function is increasing, decreasing, or constant, we describe it in terms of x, and we only use parentheses. We do not use any brackets. All right. Next one. So now we're given f of x is a parabola, in this case, opening downward. And we want to see, where is it increasing? So here, as I'm moving left to right, so I'll trace this function here. As I'm moving left to right, here, notice I'm moving upward. So that section is increasing. And then if I keep going, now as I move left to right, I'm now going downward. So that section will be decreasing. And nowhere is it flat, so there's none that will be constant. But let's take a look. So how do we describe that? Again, there are arrows. So we'll go from negative infinity, so all the way from the left, it's always going to be increasing until we hit that maximum point there. That's called the vertex. And again, the x value there is, in this case, the x value is -2. So we will say, okay, we stop when x is -2. And that's that section that is increasing. For decreasing, now we'll start at -2 because we have to go left to right so that our interval is least to greatest. So -2, and now we continue to positive infinity because we're really heading out that way to the right indefinitely. And here, I'll draw that one on as well. So again, just to recap here. So the section, as we move left to right, that orange portion is increasing, the green portion is decreasing. So the way we describe that is in terms of the x value. And over here, we have to describe this section. Well, since this parabola continues to go down and out to the left, the way we will describe that is from x is -infinity to -2, it's increasing. And then from -2 to infinity, the function is decreasing. Okay. So now we are going to go ahead and look at some factoring and some different techniques for factoring. Now, one subskill that's really important here is to know that especially for this first type here, if I have something like 5w to the third power and I multiply that by a w minus 2, well, that distributes, right? And so we get 5w to the fourth power minus 10w cubed. So that's simplifying or multiplying this out. What factoring is if we have this result, or if we have this expression, how do we get back to this factored form? And so that's what we're going to be focusing on here. Now, what we want to do is we want to see, like, for example, here we'd have to see, okay, what goes into 5 and 10 evenly? And so that's 5 goes into both of them. And then, so let's just practice. So let's say now we were starting with 5w to the fourth power, and we want to, I'm sorry, 5w to the fourth power minus 10w to the third power, and we want to factor it. So now we say, okay, well, what goes into both 5 and 10? That's 5. And what goes into w to the fourth and w to the third? And you're always going to pick your lowest power of each base. So in that case, w to the third. But when we factor that 5w cubed out, we have to decide from this first term how much is left. Well, we factored out the 5 already, and we factored out 3 of the w's, so we're only left with 1 w. Then next, let's see how much is left from that second term. Well, we factored out the 5, so it's like we're thinking that negative 10 divided by 5 is negative 2. And we factored out all of the w's. So there are no w's left on that second term. And look, we got back to that factored form. So let's try it here. We have f of x equals 2x cubed minus 8x squared. So the first thing we're going to do is find that GCF. And up above, the 5w cubed, that was the GCF of 5w to the fourth and 10w cubed. So let's find the GCF of these two terms here. So what goes into 2 and 8 evenly? Play around with it, but 2 goes into both. And then we're going to pull out the most number of x's that they have in common, which means we end up pulling out the lowest power of x. So in that case, it's x squared. So from the first term, we're trying to figure out what's left over. Well, we already factored out a 2 and we factored out an x squared. So we factored out 2 of those x's, we're left with 1. And then we have negative 8x squared. And we've already factored out this 2x squared. So we just have to find out what is left. So we divide out that 2 and we're left with negative 4 or minus 4. And all of those x squareds were factored out. So we have none left. And this is another way to write f of x in factored form. And of course, to check this, if we ever wanted to check this, all we have to do is multiply back the 2x squared in. So let's see, multiply 2x squared times another x, 2x cubed. Because really here, exponents add. We have x squared and we multiplied by 1 more x to get x cubed. And then 2x squared times negative 4 gives us negative 8x squared, or 2x cubed minus 8x squared, which is what we started with. So we just verified that that factoring actually is equivalent to our original expression. All right, B, g of x equals 12w squared x to the fourth minus 8w cubed x. Again, let's take a peek and identify what number goes into 12 and 8 evenly. So we're finding the GCF of each term. So let's see. We can go 2 and 6 go into 12. 2 goes into 8, but 6 doesn't. But let's see, is there anything bigger? 3 and 4 go into 12. Oh, and 4 goes into 8. And you can explore further, but that is the biggest number that goes into both 12 and 8. So we'll pull out a 4. And now we're going to factor out the lowest power of each variable. So between w squared and w cubed, I can pull out a w squared. And between x to the fourth and just x, I'll pull out the x. So left over from the first term, if I factor out a 4w squared x, so I factor out the 4 from the 12, I'm left with 3. The squared, or all the w's, are factored out, so I have no more w's left, but only one x was factored out. So I had x to the fourth, so 1 got pulled out, so now I only have x to the third left. Similarly, what's left from that second term? Well, I have negative 8w cubed x. So if I factor out the negative, or I factor out the 4 from the negative 8, I get negative 2. And 2 of the w's were factored out, so I'm just left with 1 more, and that x was factored out, and so we are all set. And to make sure that you pulled out all of those common factors, you can see here that the 3x to the third and the 2w no longer have anything in common. So that is our final answer, factoring g of x. And in this case, we were factoring out the GCF. Okay, last type of factoring out the GCF. Let's see what it looks like with trig functions. So if we have h of x equals 8 sine x plus 4 sine squared x. How are we going to factor this? Now this is a little trickier. Now we have to be very careful. We want to make sure we're treating this sine x as a unit. We can't split the sine from the x. It's sine x is all one unit. So we have to ask ourselves, what can be factored out between an 8 sine x or a 4 sine squared x? And if you want, of course, you could rewrite this. This is not necessary, but you could rewrite this as putting this sine x in parentheses. So you notice it's just all one unit. Okay. If that confuses you, don't rewrite it then. So again, what do they have in common? So 4 and 8, they both have 4 in common. And sine x versus sine x squared, they both have a sine x. Again, we're taking that lowest power of sine x. So from the first term, what's left? Well, when I factor the 4 out, I'm just left with a 2, and the sine x was factored out. On the second term, we factored out the 4, and we factored out one of the sine x's, but another sine x remains. And so that is going to be the factored form, which is 4 sine x times the quantity 2 plus x. Oops. Let's try that again. 4 sine x times the quantity 2 plus sine x. Okay. Let's keep going here. I will show, actually, just as another option, there's another alternative way. If that didn't really work for you, if that was very confusing, you can do a U substitution. And U substitutions are really important, especially if you get all the way through, if you're planning to go through calculus, you want to be able to do U substitutions because you'll be doing them there in different ways. So if we let U be sine x, then we could rewrite h of x as 8. Instead of sine x, I could just write u, and plus 4. Instead of sine squared x, I could just say u squared, since u is sine x. So I'm just simplifying it. Then I can do my factoring. So here, again, what's the GCF of 8u and 4u squared? I get 4u, and then what's left? 2 from the first term plus u from the second term. And then to finish up, I have to now plug in that sine x for u. So I just substitute back. So I get 4 sine x, 2 plus sine x. Either way, notice we get the same answer. So you can see the original way we did it, or using a U substitution. Both will give us the same answer. Okay, so the next type we're going to do is of the form, is if the original polynomial is of the form x squared plus bx plus c. And again, just to kind of recap, if we had something like x plus 2 times an x minus 5. Let's just go ahead and actually, I'll just, for simplicity, I'll make everything positive here. So let's multiply that out. So we get x squared, x times x is x squared, and then plus 5x plus 2x plus 10. And we can simplify that because we have like terms in the middle. And our final answer is x squared plus 7x plus 10. So what we're looking for, so notice here, if I'm looking at this as a x squared plus bx plus c, if we're now trying to start with this polynomial and we're trying to get into this factored form, we have to try and figure out, okay, well, what's the pattern here? So if the goal is to come up with 2 and 5, notice 2 and 5 multiply to c and add to b. So essentially, if we look at this form, x squared plus bx plus c, what we're trying to come up with is what two numbers multiply to c and add to b. And if we find those two numbers, we will be able to get our factored form. So in this case, if we're looking and we're saying, okay, if we had this and we're trying to get to this x plus 2, x plus 5, we say what multiplies to 10 and adds to 7, and that's 2 and 5. And then we could get that x plus 2, x plus 5. Let's see it in action. Let's take a look. So we have this, we're trying to factor x squared minus 2x minus 8. And remember, this is of the form x squared plus bx plus c. So there's no other coefficient in front of our x squared other than 1. So as a tool, we can say, okay, let's see what numbers multiply to c, in this case, -8, and add to b, in this case, -2. So feel free to pause and find those two numbers. We say, oh, it's going to be 4 and 2 but one of them needs to be negative, one negative, one positive. And so if 4 and 2 have to multiply to be a -2, we need more negatives than positives. So this will give us that factored form. These two numbers are what go into our factors, x minus 4 and x plus 2. And that will still equal f of x. And so we're all done here on this problem. But if you wanted to check it out, all you do is just multiply it out. So if we multiply that x minus 4 times x plus 2, we get x squared plus 2x minus 4x minus 8. And you can see the x squared checks out, the minus 8 checks out, and then if you simplify those two, we'll get that minus 2x. So for B, I welcome you to go ahead and just factor it in this form, or we can go ahead and try a U substitution. So I'll go ahead and show it using a U substitution. And what you want to recognize is that we have something squared and then plus, or in this case, minus 7 times that same something, in this case, cosine x, and then plus a constant. So we can let U equal cosine x. So now we can just rewrite g of x as, well, cosine squared x, we can just rewrite as u squared. And then minus 7 times u, again, we're replacing the cosine x with u, plus 12. And so we're ready, because it's of that form, x squared plus bx plus c. So what multiplies to 12 and adds to -7. So take your time, go through factors of 12. So 1 and 12, nah. 2 and 6, close, but no cigar. How about 3 and 4? There we have it. So 3 and 4, they're multiplying to a positive. So they're either both positive or both negative, But since they're adding to -7, they will both have to be negative. So we're ready for our factored form of u minus 3 and u minus 4. However, we have to make sure we substitute back and plug in our cosine x. So everywhere we see a u, we're going to put a cosine x. And I'll be clear that that's my u and 4 looks similar. There we go. So we're going to get a cosine x minus 3 and a cosine x minus 4. So their product make up the factored form of g of x. And again, you can always multiply it out and make sure that you get back to your original function. C, h of x equals 2x to the 4th minus 8x cubed plus 6x squared. This is no longer simply of this form, x squared plus bx plus c. But one thing, once we get more and more into factoring, we want to be sure that we always keep our eyes out for a GCF. So really, technically speaking, the first step, anytime you go to do any sort of factoring, the first step is there a GCF? And if there is, pull that out first. So here is an example where we have 3 terms here, and they all have a GCF other than 1. So what goes into, let's find that GCF. What goes into 2, 8, and 6? Evenly, that's going to be 2. And the lowest power of x that they all have in common is x squared. And now let's find out what's left from each and every term. So from that first term, we had 2x to the 4th. The 2 was factored out. 2 of the x's were factored out, so we're just left with x squared. Then we can do that minus 8. We'll factor out the 2 to get minus 4, and 2 of the x's were factored out. And so since we had 3x to the 3rd and 2 of them were factored out, we're just left with 1x there. And last but not least, when we factor out a 2x squared from 6x squared, we get 3. All of the x's were factored out. And now, again, we have an x squared plus bx plus c inside those parentheses. So we can go ahead and find those 2 numbers that multiply to 3 to c and add to b, in this case, -4. So, well, there's not very many factors of 3, so it's going to be 3 and 1. But again, they're multiplying to a positive, adding to a negative. They will both have to be negative. And so those are part of our new factors. Don't forget that 2x cubed, but then we get the x minus 3 as one factor and x minus 1. And that, again, that is our factored form. And if you were to multiply this out to check it, I recommend you just multiply these 2 out first inside the parentheses, simplify, get your results, and then multiply it by that 2x squared. Okay. Here is our last set of examples with factoring. So first, we have 2x squared plus x minus 3. So now we have a coefficient other than 1 in front of our x squared. So actually, I'll go ahead. I'm going to hop over to the side and do another one just to get some practice at this. So and to demonstrate it, and then we'll practice it on a So let's take a look at 3x squared minus 5x minus 2. Okay, so now this is of the form ax squared plus bx plus c. So one strategy is to go ahead and I'm going to show this star method. Now, there are other methods. There are guess and check, and there are factoring by grouping. But if those methods haven't worked for you very well up until now, this is just an alternative, but you are more than welcome to look into other methods if this doesn't quite work for you. And the only restrictions here is you have to make sure you factor out your GCF first, which we should be doing anyways, and that our A is positive. So we might have to do some adjustments if our A is not positive. So here, we're going to go ahead and multiply, or first I'll kind of show the off to the side, the form is now we're instead of just an X, we're going to use a star, and we're going to, instead of just multiplying to C, we're actually going to see what multiplies AC. So you actually have to multiply AC together. So what multiplies to AC and adds to B, so that part's the same. And whatever we get, we're going to put those numbers in the bottom now, these little bottom spots. And so let's go ahead up to that point. So we're going to multiply A and C. So 3 times -2 is -6. So that's what's going to go in on top. Okay, what multiplies to -6 and adds to B, -5. So again, take your time, push pause. And on this one, it's gonna be a little tricky. I sometimes think, oh, 3 and 2, but one would have to be positive and one negative. And so that's actually not gonna work out. So, what else multiplies to 6? Oh, we could do 1 and 6. And one will need to be negative. And since they're adding to be more negatives, since it's adding to -5, we will need more negatives. So it'll be a +1 and a -6, because 1 times -6 is -6, and 1 plus -6 is -5. So those are those two numbers, but we are not done. We cannot just go straight into our factors. What we're going to do is we're actually going to take the leading term, ax squared, and just make it ax. And so in this case, it's 3x squared. We're just going to make it into 3x. And our two factors are essentially right there. The only caveat is we reduce if they can be reduced. So notice 3x and 6 and -6 can be reduced by 3. So we divide by 3, and we get that 2x and, 1x, or just x, and -2. So the way we will write that in factored form is 3x plus 1 and x minus 2. Again, you can multiply that out and see that it does in fact work out. And I'll do it on this one over here. So we go 3x times x, 3x squared, and then 3x times -2, -6x, plus 1x, and then -2. And that gives us, when we simplify those middle terms, we get -5x minus 2, and that works out. Okay, so this is the star method. It's totally optional. I will also, just for this one, I will give you another option, which is guess and check, because especially for trigonometry, a lot of the factoring ends up being pretty small numbers. It just is not uncommon. So it's a good method to know. Or if for whatever reason you're making a mistake on the star method, it's good to have backup. So when I go and solve using guess and check, so this is another method. It's called guess and check. It's really important that we check because the way we set it up, it doesn't always work. So basically these first two terms that were in our factors need to multiply to 3x squared. And so in this case, it's pretty straightforward. It's going to be a 3x and an x because 3x times x will multiply to 3x squared. And then the last two terms of each of our factors have to multiply to -2. So we don't really know where it goes though, and that's where the check comes in. So we might try 2 and 1, and we need 1 positive, 1 negative. And now you have to check. So we multiply it out. This is that check part, and you go, oh, 3x squared, and then minus 3x plus 2x minus 2. So notice the 3x squared and the minus 2 work out because we kind of forced it that way. We chose the numbers to work that. So really what we have to verify is that these middle terms give us that -5x. And they don't, because we get -3x plus 2x is -x. So that didn't work. So I'm going to go back. That would, shows us that did not work out there. But we can use that and kind of build on it. So we can try now the 3x and the x. We'll leave those in the same place, but we'll switch the 1 and 2. And again, we don't know where positives, negatives go. So I'll try negative positive this time and see what works. So when we go to check, again, if you remember, our 3x squared is going to work and our -2 is going to work. So it's really just those inner and outer term or multiplying that we got to worry about. So -1x plus 6x, ooh, that gives us positive 5x. And now we see, oh, that is the right number, 5x. We just need to switch the signs. So we can go at this stage and just keep all of the numbers in the same spot, but change the role of the positive and the negative. And that is our factored form. And you'll see we got the same results as we did up here. So sometimes you can get lucky on these and not have to try so many times, and other times you can have to try a lot more than this. So it just depends, and you'll definitely see a lot of patterns as you get in that habit. So let's go ahead and put this into practice. So if you think you have a method down, you go right ahead. Otherwise, I'll be showing the star method. So again, that star method is what multiplies to AC adds to B. So let's do it. What multiplies to, oh, let me leave some room. We'll multiply 2 times -3 to get -6. So what multiplies to -6 and adds to that coefficient in front of x, which is 1. So that's going to be 2 and 3. 1 positive, 1 negative. But we need more positives now. So the 3 will be positive. That bigger number will be positive, and the 2 will be negative. So -2 times 3 is -6, but -2 plus 3 is +1. And because I have that 2 in front of the x squared, I'm going to now take that 2x and put it on top of those two numbers we just found. And we'll go ahead, and the 2x plus 3 cannot be reduced. So that is going to be one of the factors. However, the other factor can be reduced by 2, and we get x minus 1. So the two factors will be x minus 1 and 2x plus 3. And there we have it. And of course, you can multiply it out, check, and see that it does in fact work. Now, the check on these are optional. If you use the star method, the check is optional, not a bad idea, but not required. If you use the guess and check method, the checking is part of the process. Now, we have another type of factoring here, which is a difference of squares. So let's kind of just practice on something like x minus 7, x plus 7, okay? Oh, do a different color here. X minus 7, x plus 7. Let's multiply that out. So we get x squared plus 7x minus 7x, and then minus 49. What do we notice about the 7x's? Well, since one's positive and one's negative, they cancel out and we just get x squared minus 49. So this is actually a difference of squares. And so we're going to use the property that if we have an a squared minus a b squared, like a x squared minus 49, that can be factored into a plus b, a minus b. Or in this case, x minus 7, x plus 7. So let's take a look. Let's look at g of x equals x squared minus 25. So we might notice, oh, that's like an x squared minus a 5 squared. So that can be factored into an x plus 5 and an x minus 5. Again, if we were to multiply that out, we would see that those 5x's cancel, and we're just left with that x squared minus 25. And for our grand finale of factoring, we have h of x equals 2 tangent cubed x plus tangent squared x minus 3 tangent x. So let's go ahead. We have a GCF here. So that's the first thing. As soon as you see that cube, you think, oh, is there a GCF? Because that would be nice. And there is. So notice we can't pull any numbers out, but each term has a tan x. So I'll go ahead and first factor out a tan x. And we're left with 2 tangent squared x from the first term, just a tan x is in the second term, and minus 3 from that third term, since the tangent x was factored out. And now you can either continue on with the star method with that tan x, or we could use the u substitution. So I'll go through and finish this off and then show the alternative with the u substitution. So here, if we wanted to do this, we see that with this 2 in front of the tan squared x, this is of that form ax squared plus bx plus c. So the first thing we're going to need to do is multiply our 2 times negative 3 to get negative 6. And then what multiplies to negative 6 adds to 1. And it's actually the same numbers as we were using over there. So it's negative 2 and positive 3. And instead of putting just 2x here, we can now put 2 tan x here on both. And again, on the 2 tan x plus 3 is already simplified, but over here we can reduce by 2 and just get that tan x and minus 1. And so we're ready for our factored form. Bring down that tan x out front, and we got tan x minus 1 and 2 tan x plus 3. So that's how even the star method still works with our trig functions in there as well. But if that is just a little much, let's practice instead doing this with the u substitution. So I'm going to let u equal tan x, and I'll go from the top. So back to h of x, but now in terms of u, it's 2u cubed plus u squared minus 3u. First step, GCF, factor out the u. And now we're ready for the star method. So 2 times -3 is -6. So what multiplies to -6 adds to 1. Again, it's that 2 and -2, +3. And we drop the squared from that 2u squared, and it's 2u. And we have one factor is ready to go. The other needs to be reduced by 2 to get that u minus 1. And so we drop down that u, we got u minus 1 and 2u plus 3. And then to finish it off, we got to substitute our tan x back in. So tan x times the quantity tan x minus 1, and then times 2 tan x plus 3. And sorry, I ran out of room, but I was doing both of those methods, so it just took up some more room. So that is not only a review of factoring, but also seeing how it will be applied to some of our trig functions and expressions involving our trig functions. And I will say that for our elementary trigonometry class, C is a little advanced as far as the factoring we will see, but it's great exposure to see how our factoring methods apply to expressions involving our trigonometric functions. That does it.